All right, hello everyone, and welcome to my channel. Um, this channel is for educational purposes, and today is our 491st video that we've done on Dewey B. Larson and his reciprocal system of theory. And this is a system of theory, meaning that it is a generalized theory. You can learn its basic ins and outs, and once you do that, you can apply it to any subject that you want. So it's a glorious theory of everything that is difficult to learn, but it's way worth it. And you know, Mr. Larson maybe made a few mistakes along the way. Some of those things are being cleaned up as we speak, or have been cleaned up. But the future is bright, I believe, for the reciprocal system. I believe this is the only channel that I can find on the internet that is going into it very deeply. Almost 500 videos. Now, if you want to get the kind of the 20-minute, somewhat halfway thorough explanation of the reciprocal system, you don't watch any of my first 474 videos on this subject, where I go into the reciprocal system in a little bit of detail, at least kind of give you the ins and outs of it. But I guess from here on in, I'm going to more or less assume that you have some kind of working knowledge of the reciprocal system, because what we're doing here is basically reading Larson's books. And today we're reading from, and for the last month or so or more, we've been reading from his 1987 book, Basic Properties of Matter, which is on chemistry. But again, it's on chemistry, but if you learn how he does it with chemistry, then you can, you know, apply it analogously to other subjects. You know, he uses the same rules for chemistry that he uses for astronomy, that he uses for metaphysics, that he uses for economics. I mean, it's not exactly the same, but you plug it in like in an analogous way. Larson's Larson, he lived from 1898 to 1990, and in 1959 he proposed his two fundamental postulates about how the universe operated, and then he derived a theoretical universe from those two postulates, basically what my universe would look like if my postulates were correct. And then he compares his theoretical universe with the universe that was measured in the laboratory and compiled in tables by armies of legacy scientists. And basically, Larson's reciprocal system is also known as universe of motion. He's one of the few scientists to propose motion as the fundamental thing in the universe. Not matter, not energy, not forces, but motions. And everything is made out of motion. In particular, what he calls a scalar motion. Scalar motion is a motion that has a magnitude but has no specific direction. That's about as far as I'm going to go. If you want more detail, you can go into any of my first 474 videos on this subject. But from now, we're going to go we're right in the middle of chapter 14 of Basic Properties of Matter, which is on the basic forces. So here he is talking about the forces, you know, gravitation, electricity, magnetism, and that they are not, or you know, the weak nuclear force and the strong nuclear force, which are basically completely made up, and these are not fundamental. They are just simply kinds of motion. And so Larson gets into that here. And we went through the first section of this chapter yesterday. And I apologize about yesterday. I was so sleepy. I think I might have actually fallen asleep a couple times during the video. It's hard to tell when you're nodding off like that, where if you're not was I asleep for like 2 seconds, or was I asleep for like 2 minutes? So I don't know if there were like, I didn't go back and watch it because I was just trying to get it out at the time. So anyway, I'm quite a bit more alert tonight. So hopefully I'll be able to stay awake. Okay, we're going to start right here. There is no reason to be apologetic about these few errors and omissions. Larson's just referring to some things that he didn't get right in his first edition of this three-volume structure of the physical universe that he put out in 1959, and he's saying that now, after 28 more years, I've learned a few more things. So, present-day physical theory has been in the process of development for centuries, during which a myriad of conclusions that have been reached with respect to details of the theory or theories have subsequently had to be abandoned as incorrect. In comparison with this experience, the error rate in the development of the theory of the universe of motion is fantastically low. This is no accident, inasmuch as all conclusions in all areas are derived deductively from the same set of basic premises. Consistency of the interrelations between phenomena, the basic requirement for conceptual validity, is achieved automatically. Those cases in which the developers of the theory are having some trouble merely emphasize the easy and natural way in which solutions for most of the previously unsolved fundamental problems of physical science have emerged from the theoretical development. The review of the gravitational situation that was recently undertaken was able to take advantage of some very significant advances that have been made in our understanding of the details of the universe of motion, that is, in the consequences of the postulates. In the years that have elapsed since publication of Volume 1 in 1979, that's his book Nothing But Motion, which is mainly on like atomic physics, some organic chemistry. And that's the first volume of his three-volume set, The Structure of the Physical Universe. This is the second volume, even though it came out third. Basic Properties of Matter, primarily on chemistry. And then his third volume is called Universe of Motion, which came out in 1984. And that is on astronomy. Chief among these is the clarification of the nature and properties of scalar motion, discussed in Chapter 12, and covered in more detail in the 1982 book, Neglected Facts of Science. The improvement in understanding of this type of motion has thrown a great deal of new light on the force relations. It is now clear that the differences between the basic types of forces that were recognized from the start of the investigation as dimensional in nature are differences in the number of scalar dimensions involved, rather than geometric dimensions of space. So he's making a distinction between scalar dimensions and vectorial dimensions, or dimensions of space, dimensions of time, and then scalar dimensions. You can, or dimensions of motion. So you can have 3 dimensions of space, but you only need 1 dimension of motion to exhaust 3 dimensions of space. And so the reference system doesn't, isn't adequate to describe 3 dimensions of motion. So, though that points out some of the limitations of the stationary spatial reference system. And, that one of the reasons that Larson uses the moving reference system that he calls the natural reference system. Okay, this provides simple explanations for several of the issues that had been matters of concern in the earlier stages of the theoretical development. The significant conceptual change here is in the nature of the relation between motion and its representation in the reference system. In previous physical thought, motion was regarded as a change of position in a specifically defined physical space, for Newton, or space-time for Einstein, during a specific physical time. This physical space and time thus constitute a background or container. Changes of position due to motion relative to the spatial background are assumed to be capable of representation by vectors. In the theory of the universe of motion, on the other hand, space and time have physical existence only as the reciprocally related components of motion. And the three-dimensional space of our ordinary experience is merely a reference system, not a physical container. Furthermore, the development of the details of the theory in the preceding pages of this and the earlier volume shows that the spatio-temporal reference system, which combines the three-dimensional spatial frame of reference with the time magnitudes registered on a clock, is incapable of representing the full range of existing motions. Some motions cannot be represented in their true character. Others cannot be represented in this reference system at all. The deficiency of the reference system with which we are particularly concerned at this time is its inability to represent multi-dimensional scalar motion. This inability of the reference system to represent more than one scalar dimension of motion explains why the forces exerted by charges and masses are all one-dimensional, irrespective of the number of scalar dimensions applicable to the inherent motion of the charge or mass. Only one of these scalar dimensions is coincident with the dimension of the reference system, and the motion in this dimension is therefore the only one that can be represented in the reference system. As indicated earlier, this limitation on the capability of the reference system is the reason for the great disparity in magnitude between the basic forces. The total magnitudes of the electric and gravitational forces are actually the same, but only the motion in the dimension of the reference system is effective. In our gravitationally bound system, the dimensional ratio in CGS units is 3 times 10 to the 10th. Thus, the electric force, which is one-dimensional, and therefore fully effective, is relatively strong. The gravitational force actually has the same total strength, but is distributed over 3 scalar dimensions, only one of which coincides with the dimensions of the reference system. The effective gravitational force is therefore weaker by the effective electrostatic force, weaker than the effective electrostatic force by a factor of 9 times 10 to the 20th, or the square of 3 times 10 to the 10th. It should be noted, however, that the difference in the number of effective scalar dimensions has this effect on the relative magnitude of the forces only because it is applied to the very large value of the unit of speed, the relation between the sizes of the units in which we measure space and time. This, in turn, is a consequence of our position in a gravitationally bound system that is moving inward in space at high speed. Opposing the spatial component of the outward progression of the natural reference system. The net motion of the gravitating system in space is relatively small, while the motion in time proceeds at the full speed of the progression. Thus, we experience a small change in space coincidentally with a very large change in time. It seems to me that it would be the opposite, but I'll just try to figure that out for myself. Okay, keep going. We assign values to the units of these quantities that reflect the manner in which we experience them. And on this basis, we have defined a unit of time in the CGS system that is 3 times 10 to the 10th times as large as our unit of space. Our unit of speed is then 3 times 10 to the 10th space units per unit of time. That's in centimeters and seconds. And those are in CGS system. Larson has a different system, but he plugs it in. He's going with the CGS system for the purposes of this illustration. As can be seen from the foregoing, the magnitude that we assign to the unit of speed, the speed of light, customarily represented by the symbol c, is not an inherent property of the universe, although the magnitude of the speed itself is. The general range within which this value will fall is determined by our position in a system of gravitating objects, and the specific value within these limits is assigned arbitrarily. Any change in the unit of either space or time that is not counterbalanced by an equivalent change in the other alters the value of c in our measurement system, and the relation between the magnitudes of the electric and gravitational forces, c squared, is changed accordingly. The electric force is usually asserted to be 10 to the 39 or 10 to the 40th times as strong as the gravitational force, but this figure is based on a set of erroneous assumptions that Larson doesn't go into. So I haven't seen him go into that in another work, but perhaps he does. The further clarification of the mutual nature of scalar motion accomplished in the most recent studies has also thrown a very significant additional light on the force situation. As brought out in Chapter 12, it is now evident that a scalar motion AB cannot be distinguished in the absence of a fixed coupling to the reference system from a scalar motion BA. This means that in considering the mutual gravitational motion of two masses, we are dealing with only one motion, the representation of which is the reference system, which in the reference system depends on external factors. On this basis, the expression m prime in the gravitational equation is not a product of two masses, but the product of one mass and the number of units of mass in the interacting object. Likewise, the distance term s squared is a pure number, the ratio of s squared units to 1 square unit. Thus, the only dimensional quantity that appears in the equation, aside from the resultant force, is one of the mass terms. This result of the current study confirms the original finding reported in the 1959 publication. It likewise confirms the earlier finding that another dimensional term, a unit of acceleration, must be inserted into the equation to produce a dimensional balance. Force in general is the product of mass and acceleration. It follows that the progression for any particular force must reduce to F equals ma when all dimensions are properly assigned. The existence of the acceleration term is not apparent without a theoretical analysis because the gravitational acceleration is unity and therefore has no effect on the numerical results. The difficulties that have been previously experienced in applying the principle of the equivalence of natural units to the gravitational equation are now seen to have been due to an inadequate understanding of the manner in which the dimensionless terms in the equation should be treated when the statement of the unit equivalence is formulated. We now recognize that these terms vanish if they are given unit value in the system of measurement, in which the values of the dimensionless terms are stated, unless some structural factor is specifically applicable. However, the use of an arbitrary mass unit in the conventional measurement systems introduce a complication, as it means that two different systems of units are actually being used. As we saw in the discussion of physical fundamentals in Volume 1, all physical quantities, including mass, can be expressed in terms of units of space and time only. It follows that when an arbitrary unit is used for the measurement of mass, we are expressing the mass and the acceleration in different measurement systems. This is equivalent to introducing a numerical factor into whatever physical relations may be involved. The ratio between units, the ratio between the sizes of the respective units. Introduction of this factor does not affect the numerical balance of an equation as long as both sides of the equation contain the same number of mass terms. But in the gravitational equation, F equals kmm prime over d squared, there are two mass terms on one side of the equation, while the force, the lone term on the other side, contains only one mass term, F equals ma. In order to balance the equation numerically, a correction factor must be applied to convert the extra mass term to the units applicable to space and time. The ratio of the natural space-time unit of mass to the arbitrary mass unit is the required correction factor. Together with whatever structural factors are applicable to the equation, it constitutes the gravitational constant. The ratio of the natural unit of mass in the CGS system to the arbitrary unit, the gram, was evaluated in Volume 1 as 2.236055 times 10 to the minus 8. It was also noted in that earlier volume that the factor 3, evidently representing the number of effective dimensions, enters into the relation between the gravitational constant and the natural unit of mass. The gravitational constant is therefore 3 times that other number, and that equals 6.708, 165 times 10 to the minus 8, with a small adjustment that will be considered shortly. To apply the principle of equivalence of natural units to the gravitational equation, the dimensionless quantities m prime and d to the second power are given unit value in terms of the conventional measurement systems so that they vanish from the equation. The dimensional terms, the mass term m, and the acceleration term inserted into the equation are then stated in the appropriate natural units. 1.6197 times 10 to the minus 24 grams and 1.9971 times 10 to the 26th centimeters per second squared, respectively. The natural unit of force derived from these values is 3.272 times 10 to the second dynes. The values thus derived exceed the measured gravitational constant and the previously determined value of unit force by the factor of 1.00524. It is unlikely that there is an error of this magnitude in the measurements. It seems evident that there is another quite small structural factor involved in the gravitational relation. This is not at all surprising, as we have found in the earlier studies in other areas that the primary mass values entering into physical relations are often subject to modification because of secondary mass effects. The ratio of the unit of secondary mass to the unit of primary mass is 1.00639, which is the 1 plus the interregional ratio. The remaining uncertainty in the gravitational values is thus within the range of the secondary mass effects and will probably be accounted for when a comprehensive study of the secondary mass situation is carried out. A rather ironic result of the new findings with respect to the gravitational constant, as described in the foregoing paragraphs, is that they have taken us back almost to where we were in 1959. The repudiation of the 1959 result in the 1979 publication as a consequence of the criticism leveled against it is now seen to have been a mistake. In the light of the additional information now available, it appears that the shortcoming of the original results was not that they were wrong, but that they were incomplete and not adequately supported with explanations and confirmatory evidence, and were therefore vulnerable to attack. The more recent work has provided the support that was originally lacking. Okay, I'm just kind of trying to see where we're at here. Yeah, I'm not going to finish this chapter today. I think this might be a pretty good place to stop. Larson is, getting kind of dry here, and he's just kind of going over these units, and it's probably, not a good place to start if you are just starting with the reciprocal system. Again, I would just urge you to go back into any of my first 474 videos and look at the and listen to the kind of the summary of the reciprocal system. But just recall, scalar motion is a motion that has a magnitude but no specific direction. And you can model a scalar motion using a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other. But they won't be moving in any particular direction. They'll be moving in all directions. Every dot will be moving away from every other dot, just in the outward direction. You can also reverse the balloon, and that will be an inward motion. Those motions are analogous to what Larson calls the progression, the outward movement, and gravitation as the inward movement. And all manifestation is a matter of kind of converting that outward motion of the progression into mass, which is inherently gravitational. And so that's kind of the basic idea. But then Larson is in here kind of like chopping it up with all the different units. And this is probably more advanced than you want to really get into. I say that because it's probably more advanced than I want to get into. I understand these basic units, but I'm a little bit at a loss why he's like trying to convert from CGS units then to natural units, and why he's able to more or less, I got kind of lost here at the 10 to the 20th factor, and then, but the real factor is 10 to the 39th or 40th for the ratio between the electric force and the gravitational force, but he doesn't really explain that. So this section so far has kind of created more questions than it's answered for me. But that's kind of how it goes when you study the reciprocal system. You're not going to get all the answers wrapped up in a bow for you, because instead of having an army of thousands of scientists working on this over the course of centuries and putting in trillions of dollars of research money, you have one guy with a slide rule and no budget trying to compete with them, and actually winning in many cases. But he doesn't always answer all your questions right when you want the answers. So a lot of times he answers your questions in a different chapter, in a different passage, or whatever. And so you just kind of have to pick up a breadcrumb at a time and store them up in your mind. And then when you get the answer later on, it'll ring a bell. Okay, we're going to stop right there and get into the rest of this chapter, finish this chapter tomorrow, and then move on. So thanks for tuning in for today, and have a great